In the last video, we took a look at measures of center and measures of variation. Now we're going to move on to measures of position. How do data values rank, so to speak, with respect to other data values? Now, we're going to start with this definition of a z-score, also known as a standard score. And it basically describes the number of standard deviations that X, that data value, is away from the mean, the number of standard deviations away. And we have a formula for calculating the z-score or the z-value. And this is really the same formula. One time I used X bar and S for sample values, and the other time I used mu and sigma, but basically they're the same formula. Anytime that we have an X value that is below the mean, the z-score is negative, and if it's positive, it's going to be above the mean. And the z-score helps explain where the data value is with respect to the mean and the rest of the sample. Now that will be illustrated in this next example. Consider a data set that has a mean of 80 and a standard deviation of 4. And we're just going to begin with the basic calculation of finding the z-score for a value of X equals 70. Now, while you are getting used to this whole concept, it's very much a good idea to draw a number line with this data that they have given to you. So for this problem, I'm going to begin with a number line. I put 80 in the center. I put 3 tick marks going to the right and 3 tick marks going to the left. And I added and subtracted 4 each time I went from one to the next tick mark. Those are the X values, which I have labeled in purple with the mean at the center. Beneath them, I labeled the corresponding z-scores, representing the number of standard deviations the values are away from the mean. Notice how at the center, I labeled z equals 0. And when z equals 1, X was 84 because 84 is 1 standard deviation above the mean. Likewise, 76 is 1 standard deviation below the mean, so it received a z-score of -1. Now, I placed a brown dot on the number line where 70 is located, halfway between 68 and 72. Now, that being the case, I can just kind of tell ahead of time that the z-value or z-score is going to be -2.5. Now, mathematically, we can use the following formula. I can begin with my formula, z equals x minus mu over sigma, and I actually use the x bar and s instead. I substituted the mean of 80 and the standard deviation of 4. And when you subtract in the numerator, you get -10 over 4, which becomes -2.5. And when we look at our picture, let me draw this, we see that we have 1, 2.5 standard deviations below the mean. So the picture is consistent with the value we calculated. Now, what does this mean in words? It means that the value X is 2.5 standard deviations below the mean. When you are describing this, you need to have a direction of above or below, as well as the number of standard deviations that a value is away. So bottom line, you really want to have this definition of the number of standard deviations that an X value is away from the mean. That's what I've illustrated down here at the bottom. Now in this next example, a student scores 60 on a math test that has a mean of 54 and a standard deviation of 3. Okay, that's the math test. And she scores 80 on a history test with a mean of 75 and a standard deviation of 2. On which test did she perform better? Well, obviously 80 is higher than 60, but we're talking about on which test does she score better relative to the mean, which means I'm going to need to find a z-score for her performance on each test. So what I've done here is I've written the formula down twice. We're going to do the calculation once for math and once for history. Now in math, we're going to enter these values here. Her test score was 60, subtract away the mean, which was 54, divide by the standard deviation of 3, and you can see that 6 divided by 3 is 2. So in the math test, she scored 2 standard deviations above the mean. However, for history, same calculation, we're going to see that she scored 80 when the mean was 75 and the standard deviation was 2. Subtracting in the numerator, we get 5 divided by 2, which is 2.5. So for history, she scored 2.5 standard deviations above the mean. Putting these two together, we're going to say the following. In math, she scored 2 standard deviations above the mean, while in history, she scored 2.5 standard deviations above the mean. Therefore, her score was better in history, relatively speaking. So it was a higher score, yes, but also with comparison to the rest of the people taking the test, her score was better in history. The z-scores are able to help you to compare a student who is taking an SAT exam and another person an ACT exam. They're scored on 2 totally different grading scales. Okay, it's like comparing apples to oranges. You cannot compare them unless they are put onto a similar scaling, or as we said over at the left, a standardized scale. That's sometimes called a standard score. And so you can compare standard scores, and that allows you to compare apples and oranges, so to speak, on the same scaling, allowing you to take a person who's taken the SAT and another person who's taken the ACT and be able to score or compare how they scored relative to the mean on each of those different exams. Okay, now we're going to move on and talk about quartiles. You saw that listed at the bottom of your outputs when you do the one variable statistics here. And basically quartiles, you know the prefix quar stands for 4. The quartiles, you need 3 markers or separators to split your data into 4 parts. Now, I've automatically drawn out this data set, and it is not in order right here, but I've rewritten it in order, and you can see that we have 16 data values, 8 of which are above the line and 8 of which are below the line. So the median is halfway between the 2 central values of 17 and 17. Now the median is the same thing as Q2, the second quartile. So I'm going to tell you, wow, that should not be 13.5. I should tell you that that quartile here should be 17, or the median should be 17. I had a typo there, or a printo, so to speak. That should be 17. Now the first quartile is going to be the halfway point of the first half. So if I were to have broken this data set into 4 parts, it's almost as if I drew another line right down the center so that I have 4 groups of 4 data values each. Now, when I find the mean, the 4th and 5th item, that'll be the mean of or the middle median of the first half of the data set. That's where that 13.5 comes from. And you can see I had those 2 answers reversed when I wrote those in. So that is where my 13.5 belongs. And halfway between the 19 and the 21 is where we're going to have the third quartile, which is the value 20. Okay, so bottom line here is you're splitting your data into 4 groups. When you have an even number of data values, you have to use the rule we had for the median, the halfway between, the 2 values that are in the middle. Okay. And that's what we've described right down here in this next paragraph. And that's what we just did up above. Now on your calculator, it gives you these values. You don't have to do any of this manually. You just type them into your list. And when you do your one variable stats, right down at the bottom, there are those 3 values. And we will seldom write Q2. We will usually just refer to that as the median instead, because that's the more common name. So never again will we have to do this calculation manually. Now, notice we took our data and we split it into. If I were to look at what we call the interquartile range, that basically says subtract Q1 from Q3, and it describes the middle 50% of the data. Now that's something I want you to understand. If I'm looking at this data set, the middle 50% basically runs from 14 through 19 in this data set. We have 16 values. Half of the values are 8. 8 is 50% of 16. The middle 8 are what I have highlighted up here in the picture in pink. Now, we will see that represented visually when we get into the box plots that we're going to be looking at. Now, outliers are going to be considered to be observations that fall well outside the overall pattern of the data. Now, that will be to the far left or to the far right on a number line. An outlier requires special attention. It may be the result of a measuring or rounding error, an observation from a different population, or an unusual extreme observation. Note that an extreme observation need not be an outlier. It may instead be an indication of skewness in a data set. Okay, this next page looks pretty busy, but it's not that bad here. What we're going to be doing here is also defining percentiles and deciles. Now with a percentile, you basically are breaking the data into 100 parts. Cent, C-E-N-T, is the Latin prefix for 100. Now, when you are doing that, you basically have 99 separators into 100 parts. So we have percentiles 1 through 99, just as the quartiles split the data set into 4 parts, and we had 3 different quartile markers. When you have deciles, decit being the prefix for 10, you have 9 markers that split values into the 10 parts. Now, when a person or a score, let's say, is at the, let's just say the 83rd percentile, that basically means that a data value is above 83% of the rest of the values. It does not mean that the score, so to speak, was 83%. It is how it ranks relative to the other data values in the set. Now, the 5-number summary consists of these 5 values. And let's note that those are the last 5 values that show up when you do the 5-number summary. Notice these values at the bottom of the list: the minimum, the first quartile, the median, the third quartile, and the maximum values. Collectively, those are the 5-number summary. Okay, we can illustrate this using a box plot. It's a graph of a data set. that depicts this 5-number summary in a visual way. It is useful to help you compare different data sets, as we will see soon. It is also sometimes referred to as a box and whisker plot. So a box plot and a box and whisker plot are the same thing. So I have a data set here that we have listed. And when we go to do this, we basically want to find this 5-number summary. Now, I have already done this on the calculator. I've over here at the right, I've typed these values into the calculator, and the 5-number summary is these last numbers that you see right here, from 23 on up to 51. Okay, that matches this. Notice the high value of 51 and the low value of 23. When you are drawing these manually, you physically draw a number line. You make sure that the scaling is properly identified and that these values on the scaling are evenly spaced. Typically, what we would do is we would draw a line at the minimum value, which in this case is 23. We would draw a vertical line at the 29, which was Q1. You would draw a vertical line around the median, which is 33 in this case. You would draw a vertical line at the Q3 value, which is 42, and then you draw another vertical line or a dot off to the right. After you had done that, you would then connect the dots and draw this central box, and then draw these whiskers off to the far left and the far right. Now, we are going to have software that will do this for us, but that's how we will do it manually. I will show you how to do this on the calculator a little bit later. Now, we talked about an outlier earlier on the previous page of this screen, and it basically was a value that falls outside the overall pattern. Well, that's a general description. Now we move on to a mathematical description of what an outlier is. It's defined to be any value that is more than 1.5 IQRs below Q1 or more than 1.5 IQRs above Q3. And we will show you how to calculate this now in this list, but we'll now in a little bit do this manually. So what you're going to want to do is arrange the data values in order and find the quartiles. So what I've done here is I've taken these data values from up above and I've arranged them in order. Well, I haven't arranged them in order, but if I were, I would find Q1 and Q3, and that would be the IQR. Here we go. Our Q3 was 42, our Q was 29, subtract to get 13. Now, while we have this portion right here, let me go back over to our picture and see what we're looking at visually. The IQR is really the width of this box. Okay, that is our IQR. And notice that it is the middle 50% of the data as I described it earlier. Because when you have these box plots, you have 25% of the data in this left whisker, you have 25% of the data in the first half of the box, and then again in the second half of the box, and then another 25% in the right whisker. Well, if you add the two 25% sections together in the center of the box, that's where we get to that middle 50% of the data, which I described earlier. Now, we've just done step 2, find the IQR. The third step is to multiply the IQR by 1.5. So I'm going to take our value of 13 here, multiply it by 1.5 to get 19.5. Then, because the formula says 1.5 IQR is below Q3 or 1.5 IQR is above Q3, below Q1 or above Q3, I'm going to do 2 separate calculations. I'm going to start with the Q1 and subtract 19.5. When I do that, my Q1 was 29, subtract this 19.5, we get down to 9.5. Then I'm going to take the second part of that, and I'm going to look at Q3 plus this 1.5 IQRs, Q3 plus this 19.5. Now Q3 was 42, as you see over here, and when you add those on, you get to 61.5. Now let me show you what that looks like visually in the picture at the left, but let me actually do this at the right instead, come to think of it. I've got another one of these drawn out for you. And we have said that the IQR is this width right here. Now, I'm going to start at Q1, and I'm going to go -1 of those IQRs. Notice how that's about the same width there. And then I go another half of an IQR off to the left. Then if I were to start at the Q3, let me move that box over, Q3 and add 1 IQR to the right and then another half an IQR, it gets me to another point. These would be the 9.5s and the 61.5s, which I would call the lower and upper boundaries, or you might want to think of them as fences, and anything beyond those fences mathematically would be considered an outlier. Now, are there any data values below 9.5? No, our smallest data value was 23. Are there any data values above 65? No, our highest data value was 51. So in this data set, there were no outliers, okay? But it's a good representation. This picture, I think, really helps you to understand what an outlier is, not as opposed to just having this definition. Okay, now when you are drawing these different types of box plots, you don't want to just be able to draw them. I want you to be able to learn or glean information from them. So let's look at each of these different statements below. If the median is near the center of the box, I've just drawn a picture over here and I'm only focusing on the box. If that median is in the center of the box, then we say that the distribution is approximately center. If this median, which is the line drawn down the center of the box, falls to the left of the center, then we say that the distribution is positively or right skewed. If we look at this third picture in which that median falls to the right of the center, then we say that the distribution is left skewed. Okay, now let's talk about the whiskers. If the lines that we draw are about the same length, then we say the distribution is symmetric. I've got both of these lines about the same length. If we have one whisker larger than the other, so here I've got the right whisker larger, then it is skewed to the right or positively skewed. If my left whisker is larger, then we say it is negatively skewed or skewed to the left. So these first three statements are dealing with the median, the bar in the center, but the next statements are dealing with the size of the whiskers. Now, ideally, when you have a perfect symmetry case, you've got the median line going straight down the center of the box, and all four sections of this box plot, each of the whiskers and each half of the box, are of the same width. So that's how you actually look at the data set to understand the skewness or symmetry of the data set. Now, what I have at the right might be something that you'd want to blow over, but I think that table is very meaningful because it kind of describes the traditional way of analyzing data versus the more modern approach where we explore the data through box plots and different other types of measures. Traditionally, we use a table, a frequency distribution, and a histogram, and we find the mean and the standard deviation. And those are just numerical measures and pictures of our data set, very much in that descriptive category. Whereas the exploratory data analysis is when we start having the stem and leaf plots, the box plots, and we start looking at the median and the interquartile range. It starts to give us a different shape of information. As we learned back in chapter 2, different types of graphs can give us different information. Remember how we had a frequency histogram and a relative frequency histogram? The shapes were exactly the same. One actually gave us the counts, how many values were in each category. The other one gave us the percentage that were in each category. So when you had the actual values, you could go back and reconstruct the data set. But when you had the percentages in each category, you didn't have the raw data available to you, but it worked very well for larger data sets. So understanding that different charts and graphs and diagrams serve different purposes is a key concept here. Now, I've stated here an important point to remember is that summary statistics, such as the median and the IQR, which is part of this second column, used in exploratory data analysis are said to be resistant statistics. The median and the interquartile range are resistant. What does resistant mean? It means it is less affected by outliers than a non-resistant statistic. Less affected by outliers. We know that the mean is very sensitive to large and small values. But when you start looking at the median, it's not as affected by those extreme values because when you calculate the median, you start working your way in from the center and you ignore those values. Okay, it's the central value instead. So that's essentially what we're looking at and describing in that paragraph. And that's just an important concept to understand. Now, in this class, I'm not just testing you on your ability to do calculations, but I want you to understand these concepts that I'm describing also. Okay, now we're going to move on to how do we draw box plots on our graphing calculator. Now I've got the descriptions right here for you, but I have these two data sets already typed into the calculator. And if you guys could pause your video and do this along with me, the two data sets that we're dealing with are right up here. And the only difference between the two data sets is I replaced the 51 in the first data set with a 75. And the 23 in the first data set with a 13. So those are the only differences between the two. Now let me go over to our graphing calculator now, and let's take a look at stat edit. This is what you guys have done. You have typed in these values. I hope you paused your video. If you haven't done so, now's the time to pause it and get these values in. After you've got these values in, if you want to view your stat plots, you're going to hit second, and above the Y equals button, it says stat plot. Now you've got multiple stat plots, and I'm going to be focusing on list 2 here, the second data set. And I'm going to go into the stat plot, and the first thing you need to do is make sure it is turned on. You can see that we're inside of stat plot 1 now because it's highlighted, and turn it on by hitting enter. And then there are different choices here. I'm going to begin with this one that I've got highlighted here that's blinking, which is the standard box plot. Okay, that is a key value. And notice on the next row, I have typed in list 2. If you don't have that, you hit second and then your button 2 to make sure that is list 2. Now, in order to view your box plot, you are going to hit the zoom button on the top center of your keypad beneath the screen, and then you're going to choose choice 9, zoom stat. You can either type your 9 hit the 9 button, or you can scroll down to number 9 to select it. And when you hit zoom stat, automatically you are going to get this box and whisker diagram, or this box plot for you. Now you can see that I've got the x-axis drawn in here. I've got a note in your notes on how to turn these axes off. It doesn't bother me to have it there, but let me show you something that we can do. If you hit your trace button, the one that I'm just now hitting that turned red, notice it has a blinking cursor now at the median, and at the bottom of the screen it says that the median is 33. And you can hit your left arrow to go back and forth between, and then over to the right to go back and forth between the different values in the 5-number summary. Now that is the standard box plot. Now let's go into our box plots again by hitting second followed by your stat plot. And I'm going to go into my second one here. And this one is now going to be turned on. And let's go down to the next row, and the 4th item on that row, the one that looks like a box plot but has a couple little dots on the right, that is known as the modified box plot. And what it will do is, if there is an outlier in the data set, it will identify that for us. Now I've kept number 1 on, and I'm also going to turn number 2 on here. If I hit zoom followed by 9, notice I now have both plots on my screen, and you can see that we have an outlier off to the right side here. What it does is it identifies it as an outlier, and it draws the whisker only to the 2nd highest value. Now, we don't have an outlier on the bottom end. We only have an outlier on that upper end. Now, if I hit my second stat, you can, let's try that again, second stat. Let me hit second quit to get out of here. Second quit. Now, second stat, notice I have 2 of them turned on. If you ever want to turn them all off at once, you just go down to plots off, hit enter, and it turns all of your plots off. So bottom line, you have a way to check on your calculator whether a data set contains an outlier. And notice that that value of 75 was the outlier that we identified a moment ago. Now, if I just ask you a yes or no question, is there an outlier in your data set? You can just go look at this graph right here. Maybe I'll say yes or no, and if so, what is it? Well, then you'd say it is 75. However, if I want to have you show me that you have a little bit more understanding, I could ask you, going back 2 screens here, what are the boundaries beyond which you have outliers? And then you would say anything below 9.5 or above 61.5, or whatever those values happen to be for this particular problem. Now you will practice that in your homework. So we'll be going over that when we go over your homework with you. Okay, what I'd like to do now is I'd like to do a matching activity with the histograms that you have on the left, which are standard ways of drawing data sets or describing them, with the exploratory ones, the box plots on the right-hand side. It helps to give you an understanding of the comparison between these. Now, in doing this, I'm going to begin with the second histogram over here on the left. the one that you can identify as being very much a skewed to the right distribution. Now, which of these three at the right do you think matches with this second histogram? And I'm going to ask you to pause this video and answer that for yourself. Okay, you should have noticed that that goes with graph A up here in this corner, because if it is skewed to the right, that means most of the data is on the left. And that's what we have here. It skews off to the right with that long whisker. Now there is no left whisker, which basically means right here at the bottom, all, you got 25% and another 25% kind of all in the same place, with another 25% in the second half of the box and the last one stretching out off to the right. Now I have two more of these to compare, and they're going to match with either graph B or C. So if you guys could please pause the video again and try and match 1 and 3 at the left with B and C at the right, and then we'll check our answers in just a moment. When I look at these and I'm comparing histogram 1 with histogram 3, I notice that 3 is more so to the right. More of the data is pushed off to the right, as opposed to plot 1, where more of the data seems to be pushed to the left. And that to me really helps me identify which one. I've got a larger bulk of my data in B going with plot 1, and therefore pushed a little bit further to the right or centrally located. That would be 3 going with part C. So hopefully that helps you to see that relationship between these two different types of graphs. Okay, I've got a fun little comic that goes along with this. At least I hope you find it kind of entertaining, especially with my voices that I'll use to read this. The gal goes, "Can my boyfriend come along?" "I'm not your boyfriend." "You totally are. People. But you spend twice as much time with me as with anybody else. I'm a clear outlier." "Your math is irrefutable. Face it, I'm your statistically significant other." Okay, I really like that one. It kind of just illustrates this outlier in a fun sort of way. Let's move on to our last question before we finish off this chapter. And in this practice exercise, which I'd like you to please try and do on your own and then come back or pause between questions, use this as a resource to see how much of this chapter you've really understood. Let's take a look here. In a survey of 600 homeowners with high-speed internet, the average monthly cost for a high-speed plan was $64.20 with a standard deviation of $117. And estimate the number of plans that cost between $52.43 and $75.97. So I began by drawing a picture. Here we go. I said, here's my 6420 in the middle. And I went tick, tick, tick to the right and tick, tick, tick to the left. And I only bothered subtracting off the $11.77 and adding it one standard deviation out, because I noticed that that matched with the numbers that I needed to use in part A. And down beneath the grid, graph, I wrote the z-scores, one standard deviation above and one standard deviation below, to help organize what we're dealing with here. Now, it doesn't tell us that we are dealing with normally distributed data, but I'm going to just tell you that we're going to use that for this problem. And we're just going to leave that there for this problem. Here we go. You know that when you go one standard deviation to either side of the mean, you find 68% of the data values. That's part of this empirical rule of 68, 95, 99.7. So 68% of those values. Now, that's not what we're looking for. It says estimate the number of plans. A little bit different than a percentage. So what did I do? I said, okay, let's find 68% of the 600 homeowners. Of is a multiplication word. I wrote 68% as a decimal, moving the decimal 2 places to the left, and wrote that as 0.68 times 600, which says 408 out of the 600 homeowners had plans that cost between those two different values. Now, part B changes the game a little bit. This one says, okay, what percentage have data plans that cost greater than 52.43? Well, that's right here at the 1 standard deviation. We want that 1 standard deviation from here to the right. Well, if I come down to my picture at the left, that's going to be right where my marker is being drawn here, 1 standard deviation to the left of the mean. Now, we know that we're going to have 50% of the data to the right of center, and then another 34% when you go to that first standard deviation below the mean. So that marker that I've drawn in purple has 34 plus 50 has 84% of the data values above it. So what I did here is I said 84% of the 600 is what I'm looking for. Okay, again, 84 comes from that 34 plus the 50, 34 being to the left, the other 50 being to the right of center. When you finish that calculation out and multiply as above, you find 504 out of the 600 have internet plans that cost greater than $52.43. Now let me erase that little marker here and let's move on to the next part. The next part says estimate the number of internet plans which cost less than $87.74. Now I go up to my picture up here and I go, ooh, I don't have that on my number line, but I bet that's going to be the next value out because these problems are kind of contrived to be that way. And so that will be 2 standard deviations out to the right. And I'm going to draw my little marker down on my normal curve to be between the 2nd and 3rd standard deviations. Now this time I know I've got 50% to the left, and then I've got 2 more percents which I can add on here, the 34 and the 13.5. Or you can say the orange and the little white section to the right of it add up to 2.5% and do it that way. And that will get you to 97.5%. So I have 97.5% of the 600 homeowners will give us 585 in this category. Now part D says, let's find or estimate the number of internet plans which cost between 52 and 64. Well, that one's not as bad here because if you're looking at your picture, 52 is 1 standard deviation below the mean and 64.20 is the dead center. So you know right there on the picture that you're only dealing with this 1 standard deviation going to the left, and we're dealing with 34% of the population. So in our picture, there's our 34% that we're dealing with, and I'm going to say, I've got the wrong values here. This should be 34%. I've got 84% instead. I think I had the answer to part B typed in above here. So I'm going to need to change this to a 34 also. And my 504 needs to be erased. And if we take 0.34 and multiply by 600, we get 204 as our correct answer. I'm sorry that I didn't have that prepped properly, but 204 is the answer there. Good luck on your homework, folks.